Alright, first off, notice that I did not type this note sheet. Clearly that means I must be a loser and a horrible person, not to mention a horrible teacher. And I hope you can get past it and that it will not affect your ability to learn this material. So anyway, now that we got that out of the way, we are looking at solving exponential and log equations. So the first one here, we have an exponential equation, 5 to the x equals 9. Our goal is to solve for x. Now there's no way we can get equal bases here to solve this exponential equation like we saw earlier in the unit. So instead we need another technique. And that technique is to take the log of each side. So if I were to take the log of each side, the log of 5 to the x equals the log of 9, using an exponent rule, a log rule rather, that x as my exponent goes down in front of my log. Okay, that was one of our log properties. So from there, the x kind of comes down from the power, so we could now divide over the log of 5, which allows us to get x alone. Now if the question wants an exact solution, then it would be the log of 9 divided by the log of 5, which, by the way, if you recall your change of base formula, this would be the same as log base 5 of 9. If the question just says solve, and perhaps they want you to take it to 3 sig figs, you just put this into your calculator, log of 9 divided by the log of 5 to 3 sig figs, you're going to get 1.37. Okay, so this would be an approximate answer, whereas the log of 9 over the log of 5, or this other version, those would be exact answers. Alright, our next question wants us to solve and give our answer in the form ln of a divided by ln of b, and they tell us that a and b are integers. Don't forget, this is the symbol for integers. So we notice that in example 2 here, it's another exponential equation. Alright, we cannot get equal bases. Please don't tell me 6 is 3 squared and that we could actually get equal bases, right? So what we're going to have to do is take the log of each side, but not the common log. This right here is leading us to take the natural log of each side. So we're going to take the natural log of each side. Oops. So the natural log, 6 to the x, and the natural log of 3 to the x plus 1. Like we saw in the previous example, the power is going to come down. So x ln of 6 equals, now I'm going to put this x plus 1 in parentheses in front of my ln of 3 to keep it all together. Now we're looking to solve for x, so we need to get x alone. Now what we have on the right hand side here is 2 terms that have to be multiplied by the natural log of 3. So I have ln, or 6, sorry, I have x ln of 6 on the left side. And on the right hand side here, if I distribute, I would have x times the natural log of 3 plus 1 times the natural log of 3, or just ln of 3. So what I'm going to do now is I'm going to get my x terms on one side. So I have x ln of 6 minus x ln of 3 equals ln of 3. So all I did was I grouped my x terms on one side and my non-x terms on the other. The reason we want to do this is so that if we look on this side here where we have our x's, we can pull out an x as a GCF. So we're going to go from seeing 2 x's to only 1 x in the problem. So if I pull out an x as a GCF, I'm left with ln of 6 minus ln of 3, and all this is equal to ln of 3. Well, from there, to get x alone, I would just divide over what's being multiplied by it. So I have ln of 3 divided by ln of 6 minus ln of 3. Well, we're close to matching the form up here that it says to leave it in, but it looks like we just need to have a single natural log in our denominator. So hopefully you're thinking, okay, I know a log property that says if I am subtracting two logs like that, I could turn it into division. So 6 divided by 3. So ln of 3 over ln of 2 is our final answer. Okay, and that matches the form up above that they want us to leave it in. All right. Next example, another exponential equation where there's no way we can get equal bases. So we're going to take the log of each side. Now, because there is an e in here, recall that the natural log is the inverse of e. We care about that because it's going to cancel out the e if we apply the natural log to each side. So we're going to take the natural log of each side. Okay. So over here, these are going to cancel, and the 3x is going to fall down. You could also think of this as, if you were to use your log property, you could take this 3x and plop it down in front. Either way, you're left with 3x. And over on this side, we have the natural log of 5 raised to the 1 minus x. Alright, so let's use our log property on this side. Let's bring down the 1 minus x and multiply it by the natural log of 5, like we saw earlier. Let's distribute. Because we see an x in here, we're going to have to try to bring it over to where the other x is. Alright, so we can eventually solve for x. So we have 3x equals, we'd have the natural log of 5 minus x natural log of 5. From there, I'm going to add over my x ln of 5 term, and then I have equals ln of 5. The reason I did that was to get my x terms on the same side of the equation, so that I could now, just like earlier, take out an x as a GCF. If we take out an x, we're left with 3 plus ln of 5 equals ln of 5. So I went from seeing two x's to just one x in the problem. And I could now divide over that 3 plus ln of 5. Alright, now this is a nice exact solution. Alright, so again, if the question calls for a nice exact solution, we could stop there. Or if it asks us to find an approximate solution to 3 sig figs, that'd be 0.349. Okay, so please make note that this answer is exact, and this answer is an approximation. Okay, it's not exactly 0.349. There's other digits. Okay, that's just an approximation. Okay, next up here, now we're switching, oops. Let me try this again. Okay, so we're now switching gears. We're moving away from exponential equations and into log equations. So we have log base a of x squared equals log base a of 3x plus 4. Well, notice we're taking the log base a of the entire left side, and we have log base a of the entire right side. So when that's the case, we can de-log it. And notice the bases are the same of a and a. If they were different, we couldn't do that. But because they are the same, we might as well not take the log of anything. Okay, so what we're left with is just x squared equals 3x plus 4. This is a nice simple quadratic to solve. Okay, we're just going to factor this. So this is x plus 1, x minus 4. When you do your add multiply game. Now from here we're going to get x equals negative 1 and x equals positive 4. Now it's important to write yourself a little note here. Check for extraneous roots. Alright, these are roots that don't check out. So what you have to do is go back to your original equation where you have logs in it. Recall that we cannot take the log of a negative number, nor can we take the log of 0. So we need to plug in -1 and then +4 and make sure we're not getting 0 or a negative value that we're taking the log of. So if I plug in -1, over on this side I would have -1 squared. That's okay, that's a positive number. And over here, 3 times -1 plus 4, that's a positive number, so we're okay there. So we're going to accept this answer. Now the 4, same thing, plug in 4 where you see an x. We're not going to get the log of 0 or the log of a negative, so we're going to accept that answer as well. Okay, on to the back. Okay, so in our next example here, we see a bunch of ln's. Now, sometimes people want to use the same technique as our last example. They say, well, I see an ln in front of every term, so I'm just going to cancel them all out. I'm left with 12 minus x equals x plus x minus 5. Well, it's not quite that simple. You have to make sure you have the natural log in front of the entire left-hand side or the entire right-hand side. So in other words, I need to turn this right-hand side into a single log expression. I can do that by multiplying my x and my x minus 5 together. Recall that because we are adding two logs, we can condense it and write it with a single log using multiplication. So x times x is x squared, and then minus 5x. Okay. Well, now since we have the natural log in front of the entire left side and in front of the entire right side, we can cancel those out. Okay. So from there we're left with 12 minus x equals x squared minus 5x. So like before, let's get everything to one side. I'm going to add over my x, so that'll bring this up to a negative 4x. And I'm going to subtract over 12. We're going to factor. This is going to be, what, positive 2 and a minus 6. That'll add to negative 4 and multiply to negative 12. So we get x equals negative 2 and x equals positive 6. But again, don't be quick to just move on and say, okay, I'm done. We have to check for extraneous roots, so roots that aren't going to check out in the problem. If we start with x equals 6, if I were to plug a 6 in everywhere I see an x, okay, make sure you're not taking the log of something that's negative or 0. 6 is okay. However, notice if you were to plug in negative 2, alright, if you were to plug in negative 2 into this part right here, ln of x, you have the natural log of negative 2. Well, that's a problem. That's outside of our domain, so we're going to reject that answer. So x equals 6 is our only solution. Okay? Alrighty, a couple more here. So in our next example, notice we only have a single log. It's a log base 5. Alright, so we can't get rid of the log like we did before. However, there actually is a way to get rid of the log, and that is to use ben. So we're going to turn this equation, which is currently in log form, to an equation in exponential form. So recall this would be 5 to the third equals x minus 2, or 125 equals x minus 2. So x would be 127. Okay? If you were to plug it back in to check, notice that there's no problem with 127. Okay? On to our next question. So now we see on the left-hand side here a couple log expressions. They each have a base of 2. Because they have the same base, we can condense this and rewrite this left-hand side as a single log with a base of 2, and then we can multiply these two parts together. So when you multiply those two parts together, you're going to get x squared minus 2x, and then this is still equal to 3. So now this looks like our last example. What we're going to do now is get rid of the log by putting it into exponential form. So we would have 2 cubed is equal to x squared minus 2x, and then you're just going to solve it from there. 2 cubed, of course, is 8. Subtract it over, make it equal to 0. Okay. From there, we can factor this into x, plus 2 and a minus 4. Again, just simple add multiply game. Okay. And then x is negative 2 and positive 4. But again, you have to go back to your original equation and make sure we're not taking the log of 0 or a negative number. So if you plug in negative 2, notice that it's going to be a problem in the first part, right, where you have the log of x. So this one gets rejected. And then 4, if you plug that in, that is okay. Now it is possible, in theory, to plug in both of your solutions and have neither one work. If that's the case, then you wouldn't have any solutions. Okay, so it's possible to see that going on. You could also have both answers check out okay, or this scenario where only one of them works. Don't make the assumption that just because it's negative that it's going to automatically be rejected. Recall that we saw an earlier example on the previous page. It's actually not on this page, it's at the previous page. We saw a negative answer for x that ended up checking out okay in our log equation. Okay, so that's it for now. Thank you and have a wonderful day.